Yeah.
Right. Now we're going on to section 3 on Riemann surfaces, and so we start with actually the definition, namely what is a Riemann surface. Now, simply said, Riemann surface is a connected second countable Hausdorff space, which furthermore is a one-dimensional complex manifold. Now that's quite a mouthful, so we'll distill it into smaller bits so you can digest it a bit more. Namely, we call a set X a Riemann surface if we have a notion of what open subsets are of the set X, and that it is also connected. Moreover, that any two distinct points have that they admit a disjoint neighborhood. So if we let, for example, this be set X, we have two distinct points. We can find open subsets around these points so that they don't intersect, simply. Yeah, oh, it's supposed to be that way, I guess. If we furthermore have that it's a complex manifold, so in other words, we have that if we have two open sets, not disjoint, in other words, we have two open sets that have an intersection, like this, then with a so-called chart, namely a function homeomorphism at that sends each of these open subsets of X towards the complex plane, and to an open subset of that, of the complex plane. And we have that for both of them. Then we have that if we let U, for example, be this intersection of these two open sets, then we get that there must exist a transition function between the image of the one chart, of the one intersection, and of towards the other chart of the intersection, which thus are like these parts, and the transition function would be between these parts, and which must also not only be a homeomorphism, so not only a continuous function with a continuous inverse, but it must be a biholomorphism, so it must also be differentiable and have a differentiable inverse, and it's even differentiable in the complex sense. So that's the definition of a Riemann surface. Now we go through some examples to make it clearer. Namely, first of all, we take the Riemann sphere, which is simply the unit sphere in three-dimensional real space, where we let n and s represent the north and southern poles, respectively. And we let phi 0 and phi infinity be our charts, so of open subsets of S2 towards the complex plane. Although phi 0 excludes the north pole and phi infinity excludes the south pole. And they are given by this mapping, so they send these coordinates in three-dimensional space towards these two respective complex numbers. And through this image, we may see how both of these functions define a stereographical projection from the sphere onto the plane. Then we may also see, why does it just keeps on doing two at once, I think. Yeah, here. We have the inverse functions given by these formulas, namely that we have that each of them give a complex number x plus yi and sends it towards these respective coordinates. And note that in the numerator of each of these fractions, it's a three-dimensional vector separated by the commas. Thereby we may see that it's a bijection, and we get that transition function, so of, for example, the overlap, so that would be the sphere without the North Pole and without the South Pole. We get that it is able to be defined as this, namely, it's again with two at once, that's unfortunate. But we start with this. By rewriting, utilizing the function's definition, we get this expression, and we simply multiply it creatively by 1, namely this. Then we go on by rewriting and seeing that it comes down to this expression, and we simply divide out the left-hand factor in the denominator with the numerator, and we are left with 1 over x plus yi. And we may see this as the mapping of complex number z towards 1 divided by z. And moreover, we may see that its inverse is equal to itself, because we have that the mapping z to 1 over z has that its inverse is itself. And it is indeed a mapping of the complex plane without 0 to itself. And we also generally know that it's a holomorphic function, and therefore the transition function is also holomorphic. And therefore it's a Riemann surface. Now we have another characterization that we are going to compare, namely we take the extended complex plane, so you have the complex plane, and we add a point at infinity. And we may see that standard, like the extended complex plane, is also alternatively represented, or even called at times, the Riemann sphere. And we call the Riemann surface we just defined on the unit sphere the Riemann sphere. And we have that there is indeed an isomorphism between the two through, for example, this function capital phi of x, where x is a point on S2, and it sends x to our earlier given phi 0 function if x lies on the sphere without the North Pole, and we send it to infinity if simply x is equal to the North Pole. And again, this is a stereographic projection in such a sense. Then we go to another example, the complex projective line, CP1, and it is defined by the quotient of C2 as a vector space with addition, modulo the group of complex numbers with multiplication. So we exclude the complex number 0 in there. And we let C star act on the vector space, C2, through just scalar multiplication, quite simple. In such a sense, we get that the elements of CP1 are so-called homogeneous coordinates, which we made note with just like a regular coordinate, but with square brackets and with a colon in between. And we furthermore get that it satisfies these rules. I can use this, nice. Whenever z and w are non-zero, we get that z divided by w and 1, the homogeneous coordinate thereof, is equal to that of z and w, and is equal to that of 1 and w over z. Moreover, for all s in the multiplicative complex numbers, we get that the homogeneous coordinate of z and w is equal to that scaled by s in both coordinates respectively. It keeps on skipping. I'm not going to use this thing anymore. So now, to make it into a Riemann surface, we define these charts, psi1 and psi2 respectively, which have that the domains exclude z non-zero and w. They exclude z equals 0 and w equals 0 respectively. And we have that the one sends it to w over z inside the complex plane, and the other sends the homogeneous coordinate towards z divided by w. So simply the reciprocal in such a sense when you compare the two. So we may also see that they have quite simple inverses. Namely, if we take psi1 inverse of z, we simply get the homogeneous coordinate of 1 and z, and the other way around with psi2. And then we go on by defining an actual topology on CP1, and we do that on the board for a bit. So we define a notion of what open subsets are of the complex projective line, which we do through by first letting I be equal to 1 and 2 respectively for convenience. Then we let subset U be open, which we denote with the little circle, in the domain of psi I, if and only if we have that psi I of U is actually open in the complex plane itself. And moreover, we then take a look at, we let V be an open subset of our complex projective line. If and only if we have that the intersection of V and now we need more space with the domain of again psi I is open in the domain of psi I. And through this, we define this notion of openness. Then we can also see that if we take this, we get that if we let W equal the intersection between the domains of our two charts, then we get that this is true. Let's see. Psi1 of W is equal to psi2 of W is equal to C without 0. And C without 0 generally is open in the complex plane as you simply remove one point. Now, we moreover have that the transition function is also quite easily determined. Namely, we have that psi2 or psi1 inverse, and its inverse on the right hand side here are both equal as represented in the middle to 1 over z. So actually we get again that z gets mapped to 1 over z by both the inverses of both the transition functions. Now, furthermore, checking Hausdorff and second countability, it's simply inherited from the C2 vector space. And yeah, thereby we have that CP1 is in fact a Riemann surface. Now, we again go through the extended complex plane. Namely, we can simply see again an isomorphism between CP1 and the extended complex plane now, if we let capital psi of a homogeneous coordinate z and w be defined as psi2 if we have that w is non-zero and is actually equal to infinity if we have that w does equal 0. And furthermore, through this we also gain a biholomorphism or isomorphism, what you will, between the Riemann sphere and the complex projective line. And we may give it actually as well, like this, through our earlier definitions of capital psi, through isomorphisms with those with the extended complex plane, we get that phi inverse and psi inverse yield this function f, which maps a homogeneous coordinate to this right here. We get the isomorphism. This diagram didn't really work out, but generally the idea was displayed as earlier and as I denoted earlier. All right, having those examples done, we go to one quite bigger example, namely we go back to an example we already had, namely the complex exponential. We have that, as we saw earlier, the complex exponential is a covering space for the complex numbers without 0, so it maps the complex plane and each of these strips to an entire plane respectively, so each restriction is an actual homeomorphism. Now, what we will do is we define a exponential with a capital E and a logarithm with capital L, respectively by these maps, where we simply take that, for example, this exponential sends z towards e to the z and its imaginary part of the input actually. So we send it to a space that's isomorphic to R3, and the inverse is simply given by that. We won't go into that much further. But again, note that this was our regular setup. Simply what we actually do in such a sense is we glue these sheets together to get this surface and these mappings thereby. And furthermore, we get that this actually solves the problem posed earlier of having multiple branches for the inverse function. Namely, we get through this a well-defined logarithmic inverse over the complex numbers. And we also have this projection right here, which sends each of these separate sheets towards the complex numbers without 0. And as we saw before, these glued together sheets were actually made up of the complex numbers without 0, or multiple copies thereof. And we may moreover see that we can get this projection mapping by simply taking, it was the, we take the one component which is complex, so you know that that's in such a sense two-dimensional, and the other component, which is a real number, r, gets sent to simply z. Quite simple. And thereby, we also get that if we were to compose our projection map in phi with, for example, the exponential, we actually get that we can retrieve our original exponential function. Namely, if we take phi of this capital E x, we literally do get the regular exponential on the complex plane. And in turn, if we denote the restrictions of the capital L logarithm of to each of these separate sheets, we can get that if we take the kth restriction, for example, to the kth sheet denoted on the right hand side here, then that's actually equal towards taking the kth branch of the regular complex logarithm and compose that with phi k, which then is a restriction of phi to its kth sheet. And through these functions as well, through the exponential and logarithm function and restrictions thereof, we actually get that those define the charts on this surface towards the complex plane, and thereby we get that this surface on the right hand side is in fact a Riemann surface. And that's for the exponential and examples of the Riemann surfaces. And we actually go to a theorem, namely of the quotient Riemann surfaces. Namely, it states that if we let X be a Riemann surface and we have a group G, which is discrete and acts on our space X through a continuous, free, and proper action, then we have that there exist such functions through a maximal address, which in technical terms means simply a collection of those charts we saw earlier. We have that we can make X modulo G into a Riemann surface itself, and therefore the projection mapping from the Riemann surface towards its quotient space actually becomes a holomorphic map of Riemann surfaces as well. We will give a small proof outline of this theorem. Namely, the first thing you would actually do to prove this theorem is by showing that X modulo G is indeed Hausdorff, but it inherits that from our initial Riemann surface, so that two distinct points actually admit disjoint neighborhoods. Then that's proven through a contradiction, but we won't go into the specifics due to presentability. Then secondly, we construct charts which are actually made up of the charts that we already can have from the Riemann surface we start with. And then thirdly, we go and, conclude with our theorem that it's in fact supposedly a Riemann surface through such. Then, through this theorem, we may take our earlier given principal congruent subgroup of level n that acted on the upper half plane of the complex plane, and we get that by this theorem we have already seen that the action is in fact free, proper, and continuous. And by this theorem, we get that it's actually thus a Riemann surface, this quotient space, which we then denote by y of n, and we call, in fact, the modular curve of level n. And this is true for all natural numbers greater or equal to 3. And in particular, we have a special case for y of 1, where gamma of n is actually equal to SL2 of z. But we won't go into specifics of that because they're too technical for this presentation. Then we go to the uniformization theorem. It's actually in multiple parts. And the first part actually states something about general simply connected Riemann surfaces at that. Namely, any simply connected Riemann surface is actually isomorphic or biholomorphic in such a sense to either one of these three. So either to the Riemann sphere, or to the complex plane itself, or to the upper half plane. Whereas also note that these three are generally not biholomorphic between each other. For example, if you take the complex plane and the upper half plane, you get that the upper half plane is actually isomorphic to the unit disk, and by Liouville's theorem you get that any map from the complex numbers and that has a bounded range has to be a constant map. And therefore we cannot get that. Now, that was the first part. We go to the second part as well. Namely, it further states that if X is not necessarily a simply connected, like in the last part, but now a connected Riemann surface, which by the way is by definition, we define the Riemann surface to be already connected, but we want to emphasize that here. Then we can find the existence of a simply connected covering space of X, namely X0, through the covering map that maps X0 towards X. And if we let G be a subgroup of the automorphism group of X0 with G acting on X0 continuously at that, so that this proposition here holds for all G, we get that pi composited with G is still the same as just applying pi. That then X itself, our connected Riemann surface, is isomorphic to the quotient space of X0 and G. And that X0 itself, again, by the previous theorem, is isomorphic to either one of these three. Now, we won't be going into any proofs regarding the uniformization theorem. Matthijs Raumann, in his thesis, didn't do that either. He simply stated it at the end of it. He did refer to a paper which was 40 pages long, and that paper actually in its entirety was supposedly the proof of this uniformization theorem. So if you want to read it, let me know afterwards. I'll give you the link. Then we get one last nice result through this uniformization theorem for our modular curve of level n, namely that the canonical projection mapping from the upper half plane towards the modular curve of level n is in fact a covering space and a holomorphic map of Riemann surfaces. And furthermore, that the upper half plane is also a simply connected covering space for the modular curve of level n, whenever n is a natural number greater or equal to 3. And that was our presentation. Thank you for listening.
Dank u wel.